Hello everyone, this is Minyoung Kim in George Mason University. Today, we'd like to present our paper, Location-Aware Adaptation of Augmented Reality Narrative. The recent popularity of augmented reality device has enabled players to participate in interactive narrative in real-world environment. However, assigning location for story events is non-trivial and demanding. In this paper, we propose an optimization-based approach to automatically adapt narrative to real space for AR experience. Our approach assigns the comparable location to story event and synthesize a navigation graph to guide the player through different story branch. First, I will explain the overview of our approach. Given a story, we represent it using a tree structure. Based on the story tree and a map associated with different zone types, our optimization-based approach distributes the events across the map, taking into account the location comparability of the event and the player walking experience. Our optimization goal is to assign location to the story events so that the events are reasonably distributed in the real world for AR experience. Here is the cost we use to solve this problem. Our primary goal is to ensure contextual compatibility between an event and its assigned location. For example, the event "Talk to a car salesman" will be appropriate for parking lot rather than the classroom building. To do this, we classify the map into multiple zones and evaluate that how well each vertex of graph G fits with their associated story events. Other goals are about the walking experience. So by using walking distance cost, we minimize the total walking distance throughout the story. But at the same time, we balance the walking distance between consecutive events so that they did not overlap or get too close to each other. Here is the effectiveness of our cost consideration. With the location comparability, events are distributed at the location with comparable zone types. With the walking distance cost, the mean walking distance decreased. With the regularization cost, walking distance between adjacent events becomes similar. Here is the example optimization process. With the cost we mentioned earlier, our approach searched for a navigation graph that minimized the total cost function using a Markov chain Monte Carlo method. This is AR walking simulation through a synthesized navigation graph. A player starts from assigned location events A to the location events B. The player can then choose to walk from event B to event C, or choose another story branch and go from event B to event D. Now I will present our experimental results. We tested our approach in several real-world locations. For each result, our approach distributes the story events compatible with the zone types. This is the example of zone type. In the center of city area, there are several different zone types, which are hotel, parking, company, and so on. In the initial stage of optimization, all events nodes are randomly distributed, but as the optimization process goes on, the navigation graph placed each node in the appropriate zone type and the reasonable walking distance. In the Tokyo International Forum, Events app is expected to take place in a working zone and thus happen near Grand Tokyo South Tower. Next is the result near the Hong Kong Convention Center. In the Hong Kong Convention Center, Event J is packed on institution zone and happens near the convention center. Here is Marina Bay Sands, Singapore. In this result, Event A is packed on institution zone and happens near an art school. We extend our approach with an automatic zoning inference method based on the autoencoder to replace the input of fixed zoning maps. The inferred zones types include buildings, parks, and roads. Here is an example of synthesizing a navigation graph based on the inferred zone. Each node has event type, for example, building, park and road, building exclude park, or park or road. We also extend our approach with additional constraints to handle special scenarios. Designer may specify an event center around which the story events will be distributed. We showed results for 3 specified event centers. We also consider the visibility of a landmark, which can facilitate wayfinding and thus favor locations from which the landmark can be seen when distributing events. In this example, events are distributed considering the CN Tower's visibility from the event's location in Toronto. We tested our approach using 2 additional stories of larger scales. The Dinosaur World AR story has 20 events and 30 story branches, and Exterior Star Wars AR has 38 events and 45 story branches in total. The result shows that our approach can scale and accommodate more complex narratives. Since our work focused on the location-aware narrative adaptation, we conducted an AR user study to validate the effectiveness of the location compatibility cost. In this user study, we asked participants to wear an AR headset and walk through 2 different paths on a map. One path was synthesized navigation graph that considered all costs, and the other was synthesized navigation graph that did not consider location comparability cost. Using a paired t-test, we found that participants thought the story made more sense with the all-cost path. We also asked a human designer to manually assign the location to event in the medium-scale story. The results suggest that our approach can significantly reduce the workload. That's it for our presentation, and thank you for your attention. If you have any questions, please email us. We would be happy to answer them.